Hello, my name is Daniel Hudson, and I'm presenting Physics 2212, Lab 2. In this lab, we were charged with continuing the analysis that was done 2 weeks prior in Lab 1. For Lab 1, we created 2 charged lines of tape by ripping a piece of tape quickly off a table, which caused an accumulation of electrons onto that tape. So we had a negatively charged piece of tape. These tapes were held at a distance from each other, and so that one was suspended over a small chasm, and another was brought up beneath it, so the distance at which the 2 tapes were repelled could be measured. This is then used in the analysis to determine the charge on a piece of tape and the magnitude of the electric field. So the physics principles with this rely on the electric field. The electric field is the region around the charged particles where it can exert an electrical force on another object. So in this case, we're looking at the electrical field around the charged particles on the piece of tape, and we're looking to see at what force does that cause a measurable. At what distance does that cause a measurable force on the other charged piece of tape? But to calculate the electric field, we're using an equation like this for a line of charge. In Lab 1, we used the equation for point charges, which is significantly simpler, but also less analytically correct. So while I didn't actually evaluate this equation because I used a computer model, this is the type of equation you could use to determine the electric field around a line of charge. The other key physics principle to my model was Newton's second law, which states that force is equal to mass times acceleration. Because we were looking at where the pieces of tape repelled, when the piece of tape on top jumped up, you could see where it rested at maybe the top of its arc was where the net force was equal to 0. So that's when we could tell that the force of gravity was equal and opposite the force of the electric field. So that was important to the calculations. So here's the most important coding pieces from the model. On the left side, there are the constants and then the electric field. This is the calculation for electric field based on point charges. On the right, you can see how these point charges were broken up into 10 small pieces, essentially 10 small parts on each tape, and then were calculated point by point using a for loop to determine each of the point charges on the bottom piece of tape, their effect on the top piece of tape. This was then output as a model here, and as you can see, the red dots represent the small sections of the top piece of tape, and the blue dots represent small sections of the bottom piece of tape, and the green arrows are the individual electric forces on each point charge, on each small point coming from the blue tape. This is then calculated in an overall electric force represented by the white arrow, which is equal and opposite the yellow arrow, which represents the force of gravity. So as you can see, that the analysis is different between this one and Lab 1 because Lab 1 was focused on using the pieces of tape as a point charge, and in Lab 2, as we used them as a line of charge, we got a slightly different overall charge for the tape. Here, let me just go back so we can focus on that here. The charge of tape here was 3.369 times 10 to the negative 8, which is somewhat bigger than the charge we calculated in Lab 1, which goes to show that this lab was probably a bit more accurate in calculating the electric force because it was able to incorporate more of the the environment and the overall charges along the piece of tape rather than narrowing down to one single point charge. So this is useful moving forward in calculating physics and electric fields because we're more likely to deal with electric fields spread over a line or a disk or this sort of thing rather than in a single point. So thank you for listening.